Yaozhong. Okay, where's me now? Thank you. Hu from the University of Alberta. Yaozhong will talk about asymptotics of the density of parabolic Anderson random fields. I'll look you up, Yaozhong, just to have some idea of what you've been doing. And I've noticed a few things. You know, you've published lots of papers, including the book on fractional Brownian motion. And I also noted that you were a student of Paul-André Meyer. So that's for me, it's quite a connection there. But anyway, thank you very much, Yaozhong. Please go ahead. I'll turn off my camera now, and I'll turn it back on 5 minutes before the end, just to give you a hint. That's
okay. Thank you.
Thank you.
Okay. Okay. Thank you so much for the invitation and for the introduction, and also for giving me a chance to talk some of my work here. So I will be very, very happy to get some comments from you. So any comments, any suggestion will be very, very, very much appreciated. So the title of my talk is this asymptotics of the density of this parabolic Anderson random field. So this is some kind of density of random variable obtained for given by this stochastic PDE. So this is a joint work with Koale. So he's a postdoc now at somewhere in Germany. So this is the work is based on. So it's published now, but it finished some time ago. Okay, so here is the outline of my talk. So I will talk about equation. So what's the equation that we obtain? So why people start this equation? So in this equation, so this is stochastic partial differential equation. So the noise is given by some Gaussian noise, more generally Gaussian noise. And the equation is not well defined. So we define what's the mean of the solution. And then we started some property of the solution, like the moments bound and the tails, okay, or tail probability and the tail probability density also. So the main tool is this Malliavin calculus. So I will say a little bit about the Malliavin calculus also. So the main equation is this. So you want to find the u, so a function of t and x. X is in a dimension, d-dimensional, and this is the partial derivative. This kind of, if we consider this equation, is a heat equation. So people call it this heat equation. Okay, so but we have because we are on probability, so we add some noise here. Okay, so this is the noise W. So here this is Laplacian operator. So this delta is Laplacian operator. So because we are from probability, so we put 1/2 here. So for the people who are studying PDE, pure PDE, maybe people don't put 1/2 here, because we put 1/2 here because associated with the Brown motion. So why we start this equation? So this equation, so it's relevant to the so-called Anderson localization. So Anderson is someone from this physics, so who got the Nobel Prize sometimes. I don't remember the year, so maybe 70s or something. Okay, so, and this is related to the so-called KPZ equation. So if you let, because you can prove that when the initial condition, if this is positive, or I'm sorry, this is positive, for example, if this is positive, then the solution UTX is also positive. And you let HTX equal to the logarithm of this, the log, then the equation H will satisfy this equation. Okay, so you have this gradient square here, and the W is the same W. Okay, so so I will explain what is Gaussian noise more later on. Okay, so we see this equation first. So this is called the KPZ equation, and this equation was studied by many people, and there are some difficulty here, and it's harder to find what's the mean of the solution and what's the mean of this. Okay, so when this is space-time white noise, for example. Okay, so there's one very famous paper by this Martin Herr, and so this is a very long paper, and I think mainly because of this paper he got the Fields Medal some time ago. Okay, and in fact this equation was started a long time before this kind of this, because purely from mathematical point of view, or from this just a pure mathematical interest. Okay, and why? Because this equation is very simple, but it's not trivial. Okay, so for example, if you don't have this u, then this is some kind of trivial, so the solution can be obtained, and it will be a Gaussian also. But if people still started the solution of this equation without this, but it's Gaussian, but people started something more deeper property of this solution. Okay, but with this u here is more complicated. So this is called the multiplicative noise. So people call this equation with multiplicative noise. And the w, so now we explain what's w. So w is the Gaussian noise. Okay, so what's the Gaussian noise? So let me explain here. Okay, so here the noise, I would assume something more. So first you have to know what's the Gaussian random variable. Okay, Gaussian random variable is given by this. Okay, and you have more than one dimension, then the Gaussian noise, the Gaussian random variable is given by this. So the density is exponential of some negative of some quadratic form of x. Mu and sigma are some parameters. Okay, mu is the mean of this process. Sigma is the covariance. So for a Gaussian random variable, it is so to give a Gaussian vector, so you only need to give the mean and give the variance or covariance. That should be enough. Okay, and so in the noise there, so we assume the mean is always equal to 0. So we mean 0 means the mean 0 means the mu is equal to 0. So the covariance only depends on one parameter, which is the covariance. Okay. So so now we assume the Gaussian noise. The Gaussian noise first is a Gaussian random variable. Okay, Gaussian field. So we call this Gaussian field. So this Gaussian random variable depends on one parameter r for the time, and the y space. Okay, so so this is for any finite, for any given time and given y point y1, y2, yk, then w r1, y1, w r2, y2. So this is joint Gaussian, and the covariance is given by this. Okay, and the mean is equal to 0. Okay, so this is very defined. Of course, you have to say so under what condition on this you can find such Gaussian. Okay, so this Gaussian is very defined. Okay, now so the noise, so because the noise is just a derivative with respect to r and with respect to y. Of course, so for generally, for example, if this ground motion or ground sheet, the derivative does not exist. Okay, the mean of this does not exist. Okay, so this makes things complicated. Okay, so this has no meaning. Okay, but formally we can say the covariance of this is given by this. So R is given by this. Usually we assume the noise is the time stationary and the space homogeneous. Okay, so this is homogeneous, or time is also homogeneous, but we call it a time in time we call it a stationary. Okay, so we assume that this lambda, so this one is for S and R bigger than 0. So this Y and Z can be in ORD. Okay, so and for this lambda, we assume that is given by the Fourier transform of some measure. Okay, so if this Fourier transform on some probability measure, then it's always given. So this is always the covariance of something. Okay, you can always find it. Okay, so now this one does not exist, but here in the equation, so we have this. So if W dot does not exist, so you cannot expect the derivative of this exist. and the derivative of the Laplacian second derivative of this u exists. Usually this u and u has the same singularity as this, okay? So this one does not exist, this one does not exist, this one does not exist, this one does not exist. So all three of them does not exist. So this way, so this equation has a sense, okay? So if the equation, if only one of them does not exist, then the equation you can make a sense out of it. But if three of them does not exist, then you can see I can make sense of this equation. So what's the meaning of the equation? What's the meaning of the solution? So we also assume, of course, we also assume the time has this property, okay? So we are going to talk about the assumption about this covariance structure, okay, the noise. But what's the solution? So what's the solution? So here we assume this, so this has no meaning, okay? So this is given by this gamma, so now this is given by this. So R has this property. You see, when R equals to 0, so gamma 0 has some infinity, okay? It may be, so this is a noise, here have some infinity. So this is bigger than 0. I'm sorry, I got something wrong. This should be beta, okay? Oh, this can be alpha 0, okay? And for the noise, for the space, so that is for time. And for space, we also have some singularity, okay? Okay, so this is and sometimes for space-time-wide noise, we can also assume that the lambda to be a Dirac delta function. So it can be, it may not be a function, but a generalized function, okay? So this is the case when this alpha equal to 2, or alpha I equal to 1, okay? Okay, so now, as I said before, so this has no meaning. So what's the meaning of the product? Okay, so this has no meaning, this has no meaning, then what's the solution? And first we know that if you consider this heat equation with non-homogeneous term, then the solution of this equation can be written by this, okay? It can be given explicitly. So this is called the Duhamel principle, okay? So Duhamel principle. So here, this U is completely, you can solve this equation explicitly by using the method of Fourier transform, for example, okay? You take the Fourier transform and then you inverse the Fourier transform, then you get this, okay? So this P is given by the transition probability of the Brown motion, or this is also called the heat kernel, okay? So this is also, so this one is also the transition probability density of Brown motion. Okay. So so this equation is given by this. So now if this is U, so in this equation, this F is given by this. Okay, just replace this one here. Put a U and the W dot SY. W dot SY, you integrate with this. So you can define the stochastic integral. Okay. The stochastic integral, then the solution, if this one is this F, then the solution can be given by this if this is known. Okay. Okay. So this one has no meaning, but if you take the integration, then it may has a meaning. Okay. So you can define the stochastic integral with respect to the Gaussian field. Okay. This one, there are many definitions of this. Okay. You can define Stoyanovich integral or Skorokhod integral. Okay. We use the Skorokhod integral. Okay, or Ito Skorokhod integral, some people say, okay, Ito Skorokhod integral. So if this one is known, then you have this, but now this is also contains unknown, okay, you also contain unknown here. So this is another, is an equation, but this equation, you can make a meaning, you can make sense of this equation now, okay. So you see, if this one, if the stochastic integral of this is well defined, if this is true, then we say you satisfy this equation. we call this U. If you satisfy this equation, then we call this U is the so-called mild solution to this equation. We call it the mild solution. Okay, mild solution to this equation. If you satisfy that equation, okay. So this equation has no meaning, but you take the integration form. So like a stochastic integral, W dot has no meaning, but you take the integration form, then you have meaning. So this is the same thing here. Okay. So so this is called a mild solution. So now we want to start the existence and the uniqueness of this equation and start the property of this equation. Okay. So of course here you have to know how to define the stochastic integral. Okay, the stochastic integral is just like before. So if G is of this form, okay, if this is adapted, for example, if this one is W is wide in time, then you can define this one as this. So for any W, okay, for any W, okay, you don't need this to be a Gaussian process or anything. For any function, you can define this stuff into as this. So if this is simple function, okay, so the question is how to extend this to more general function, because for example, the solution may not be of this form. So how to define the stochastic integral for that? Okay, so then how to get to the limit? Then to find to extend the stochastic integral to more general function rather than this elementary process or step process, some kind of step process or simple process or elementary process, we call it. Okay, so how to extend it? So you have to find the square of this, and then to find some isometry formula and use that one to get the extension. Okay, so this one, so when the time noise is wide, then it is easy. Okay, for general one, it is more complicated. Okay, but we assume that this is so this one is easy. Okay, if this is noise. Okay, so after we define the stochastic integral, then we call this one U is the mild solution of this. Then of this equation, if you satisfy this equation, okay, so this is what I said before. Okay, so now about the existence and the uniqueness, there are many. So until now, there are many results. Okay, on this. So for example, if there's a noise, if the covariance structure of the noise has this property. Okay, if the covariance structure has this property for the time, you have this. Okay, so this the noise, the covariance is given by this. Okay, the covariance. So in this equation, so if the covariance of this is given, then the solution is given. If the initial count is given, okay. So there's nothing else. There's no other dependence. Okay, so the only dependence is about this gamma and the lambda. Okay, so the space, the time covariance structure and the spatial covariance structure. Okay, so this structure, as I said, depends on the time, the difference of the time, difference of the space. So it's homogeneous in time, homogeneous in space. So if this gamma satisfies this property for some zero, okay, for some zero between 0 and 1, so this alpha 0. Okay, and if lambda satisfies this property or this property or one of this, so one of these three conditions, okay, or this property, okay, then you can show the existence and the uniqueness of the solution. Okay, so of course here, so when gamma is in that form, then gamma is not of this. Gamma has no this property, but you can still define the stochastic integral. Okay, it is easy. Okay, so and also under the conditions that I gave before, the existence and uniqueness of the solution, it is known. Okay, so and also we have not only that, people also know that the moments of the solution is a random variable. So moments has this property, okay? So you can find a constant. Maybe you have also put a constant here. You also put a constant here. The moments, you can find a constant C, which is independent of this T and K, okay? So when K go to infinity, it go to infinity like this, go to infinity like this, okay? So alpha 0 and alpha is so alpha 0 is the spatial, is the time, from the time covariance structure. And this alpha is from spatial covariance structure. So you have this bound estimate. You see, so we do not know exactly the constant here. Okay, C prime and C, but this one are the same. The lower bound, the upper bound are the same. Okay, so these are the same. When t goes to infinity, if you take the logarithm, okay, and if you then you get the exact bound. Okay, exact exponent. Okay, and when this is a delta function, we also have that. Okay. Okay, so this is given in the paper some time ago with this David Niella and Sam Tinto. Okay, so we obtain. So the main idea is to use the. So the main tool is to use the Feynman-Cast formula. Okay, and also with some other technique. Okay, so from this one, you can get, so this one, you have the moments bound, then you have this, the tail estimate. So when A go to infinity, so U bigger than this, so when A go to infinity, what's the tail? So this will go to 0, okay? So when A go to infinity, this will go to 0, but how fast it will go to 0? Then it is given by this, and you see it's logarithm. So this U is not a Gaussian. So first, you know, this is not a Gaussian. Okay. So it is not even not a log normal. Okay, but it's log normal, but with this kind of exponent. You see, the exponent is also the same. Okay, so this exponent is the same. So the lower bound and upper bound is the same. Okay, so we have this kind of property, and for the upper bound. For the upper bound, so you can use this moments bound plus the shape inequality, okay? So plus the shape inequality. Then it's easy to obtain this. But for the lower bound, it's more complicated, okay? So this one, this lower bound, so you have to combine this lower bound and the upper bound to obtain this lower bound here, okay? So this lower bound is more complicated. And you have to use something called the Palais segment inequality. Okay, so you have the lower bound for this, you have the upper bound for this, you have the lower bound for this. Then you can use this one to get this. Okay, so fortunately we get that the same. Okay, that's the same. You can also get the left tail. Okay, so for example, this when when the initial condition is positive. When the initial condition is positive, then I'm sorry, this is terrible. So when the initial condition is positive, then U is also positive. So when this R goes to 0, so this will go to 0 when R goes to 0. Okay, so but how fast it will go to 0? Okay, how fast it will go to 0? Okay, so we also have this, but this bound may not be the best, okay, may not be best. In fact, some people, so when the initial condition is delta function, people found that the exact this equal to something, okay, then it is equal to something. So this is the work of this Amir, Colvin, and Quaster. They found the exact stuff, okay. So for example, they let this one equal to this, so this is given, okay? And U is the solution. You take the logarithm and you put this one. So this is the same as this U, T, X, Y, less or equal to something, okay? you compute this probability. So this one is the same as compute this kind of probability when this go to 0. So when s go to negative infinity, then this will go to 0. Okay, this go to 0, then this go to negative infinity. So how far? When this s go to negative infinity, this will go to 0. But how fast? They compute this f. So the computation of this f is very complicated, but I don't know if the formula is useful or not. So they first they compute this every function and they compute this the kernel. Okay, from this kernel you can define an operator k sigma xy fy. So this is some kind of operator. Okay. Okay. So this operator is a linear operator. You can find the determinant. Okay, you can find the determinant of this, and then this f is given by this. Okay, determinant. But how to compute all of this and how to compute this integral? And this is some contour integral. Okay, so anyway, they have a formula, but I'm not sure. But some people use this formula to obtain something. Okay, so I think their student they continue to work on this formula and they obtain something more precise about this. Okay, but you have to do some very better analysis. So in this talk, so what we are going to do, so for example, ut is a random variable for any given t and x. This is a random variable because wt x is a random variable. So random variables in probability theory. So random variable means that this ut depends on omega. So we never write on the omega. Okay, so you always remember everything depends on omega. Okay, so almost everything, but not for example, this one does not depend on omega. Okay, so utx is a random variable. Okay, so this random variable, so for example, in probability, in the elementary probability theory of first year student, for example, we have two kinds of random variable. One is discrete, another one is continuous type. Discrete type is something like the possible value of this random variable is given by this, and the probability that take this value is equal to this. So this is positive, and the sum of them equal to 1. Okay, so this is a discrete random variable, finite value random variable. Okay, you can also count value. Okay, but is this random variable continuous type or discrete type? Okay, so what's probability density of that? So if this is continuous type, what's probability density? So probability density means this. So this one belongs this. You have probability. Can you find the ptxy for txy is this one? Okay. Can you find a function of y so that this one is equal to this? For example, if this one is equal to, for example, the probability of a less or equal to utx less or equal to b. So this is less. Okay. Is this one equal to this ab rho t xy dy? Can you find a rho like this? Okay, so this a can be the interval. Okay, so when probably always like this. Okay, so if you can find the y, so when y go to infinity, it will go to 0. Okay, because this is integrable. This one is always positive, and the integration equal to y. Okay, so this means that when y go to infinity, this will go to 0 because the probability density function. But when y go to 0, so it goes to 0 like exponential or like what? Okay, so we want to know that. Okay, so another question is that when u0 is positive, then this one is also positive. So this means that the probability density function is supported on this 0, 1. On this 0 to infinity. Okay, so this means that when y less than 0, so this is equal to 0. Okay, so now you want to ask, so when y go to 0, is this go to 0 or go to a constant? Okay, is it possible that go to constant? Okay, so because you can find the probability density function so that on half line, so this is and not for example e negative x. Okay, so this is 0 to infinity. Okay, so this can be a probability density function. So when x go to 0, it go to 1, not go to 0. Okay, not always go to 0. Okay, And if this go to zero, how fast it will go to zero? Okay, how fast? So we wanted to answer this kind of question. Of course, if you know the exact form of this, it will be great. Okay, but it's very, very hard to find the exact form of this, in particularly for general noise. Okay. Okay, so here is now. So I'm sorry. So this is as prepressed now is equal to 2. So we always is all just publish. Okay. So we can show that this one exists. Okay, and when y go to infinity, so when y go to infinity or sufficient large, then this one is less than this, bigger than this. Okay, so when y go to infinity, so it's log of something. Okay, log of the constant here. Okay, you can put this constant. You can put this constant here even. Okay, so because this log is log plus something. Okay, so this one. So this one is the same. So log of y, the exponent the same, and when t goes to 0, so this is also you also have this. So this C1, C2, all of them does not is some kind of universal constant. It doesn't depend on t, does not depend on y. Okay, so this constants. So first we have this kind of estimate for the density. You see, when y go to infinity, so our estimate of this is sharp. In some sense, it's sharp because this exponent are the same. Okay, so this exponent are the same. Okay, so this one does not care because here is more important. You take the logarithm, then this one is more important. Okay, so this is the okay. So we have this one. I'm sorry here. So I didn't change this one. Okay. So now for smaller x, when y go to 0, then what it looks like. So when y go to 0, then we only have this. So we only have this. I don't know why it's 1 something. Okay. So when y go to 0, then we only have the upper bound. So we don't have the lower bound. Okay, so this is the square, not so we only have the square. We don't have something like this. Okay, so we are not sure this one is the best. So this exponent is the best or not. Okay, so we don't know. So for the lower bound, so this is what people call the small probability, small ball probability. So this one is more complicated. So it depends on the entropy and the computation is more complicated. Okay. So now I will give you some idea how to prove it. So what is our idea? So I'm not going to give you details. Okay. So the details is more complicated. So the tools that we are going to use is the Malliavin calculus. Okay. The Malliavin calculus. So Malliavin calculus, many people study the Malliavin calculus. So even in the math science net, there's one, I think there's one section or one subsection called the Malliavin calculus. So it's some kind of very important. And so in the area of Malliavin calculus, there are also many big names. For example, it's Watanabe, Skinner, Zakai, and many people there. Okay, so David Nuala is also some leading expert on this Malliavin calculus. His book is very famous. Okay, so many people use his book. So I also wrote a book about this Malliavin calculus. So, but I don't call it Malliavin calculus because analysis on Gaussian space. Okay, so Malliavin calculus, I think there's some kind of some people call it Malliavin calculus, and some people are not happy to call it Malliavin calculus. For example, Malliavin, he has I think a classmate called Paul Cray. And so in one lecture, I heard when I was a student, this Paul Cray give a talk and say, people should not call Malliavin calculus. It should call Clay calculus. he said that he wanted people call Clay calculus because he said in his paper that paper which is published before Malliavin's paper, and he already introduced this kind of calculus. Okay. And like my friend Ustinelli, and he called this there's something called the Malliavin derivative, and he called it the Gauss-Sobolev derivative. I think it's some kind of Sobolev derivative, the Wick derivative, but I think Gauss has more introduced there. So Malliavin introduced one, I think in the his paper is published in 1976, but in Gauss' work, I think he published the paper in 1967. Okay, he already has this kind of Malliavin derivative there. Okay, so the book has this kind of, so this I like this. This is called some Chinese probability there. Okay. So what is Malliavin calculus? So Malliavin calculus is about is different than the Ito calculus. So Ito calculus is about the derivative on this t. Okay. This is Ito calculus. So Malliavin calculus is, so you have a random variable. So depends on omega. So the differentiation with this omega is called this Malliavin calculus. Okay. So usually for many, so first, functional of Brown motion is called the nonlinear functional of Brown motion. For example, you want to study this kind of Wiener functional. Okay, like this Wiener functional, the super of the, so this is a random variable. So this is random variable, this is random variable. So this random variable may be differentiable, but this one may not be differentiable. Okay, so even like this, so I didn't, maybe I didn't put it here. So Malliavin calculus is some kind of a nonlinear analysis or nonlinear function analysis. So in nonlinear function analysis, you have some kind of Gaussian derivative or Fréchet derivative. Okay, so you have this kind of derivative. So there are many works on this nonlinear function analysis. Okay, but when you apply the Fréchet derivative or Gaussian derivative to this kind of equation, so xt is also a functional of this b. Okay, is b, but this functional is not differentiable. It's not continuous on this b, not continuous on this b, but still you can talk about the derivative. So this is the contribution of this Malliavin calculus. Okay, so it's not a function. So it's different than, it's more than this Gaussian derivative or Fréchet derivative. Okay, so Fréchet derivative differentiable. If a functional is differentiable, Gaussian differentiable, then it must be continuous. Okay, but here you don't need it to be continuous. For example, this functional is not a continuous function of b. So this functional is not continuous. So even the solution usually is not continuous, but you can still talk about the Malliavin derivative. So Malliavin derivative means you take the derivative on some direction, not all direction. Okay, so you find the derivative of this for some direction h. Okay, but not for all omega. Okay. So this is the derivative. So in Malliavin derivative, so how to define the Malliavin derivative? So you define the Malliavin derivative like this. Okay. So first you define it for this cylindrical function, for some simple function. Then you define this by using the chain rule. Okay, so the only thing that you have to define is how to define the derivative of this for so this R, for example, R. So this is just define the HT. Okay, so you just define this, and then you can use extension theory to define every. So you use the chain rule. So you ask this is a different. This is really a differentiable derivative operator. Okay, you need this one to be the derivative operator. So derivative operator means that you have the chain rule. Okay, it has some kind of chain rule. Okay, so you can define derivative, but in some direction you can compute the derivatives. For example, you can use the Kerr suspension and you find the derivative. So in Malliavin derivative, I'm not going to give you because I'm running out of time. So there are many things. So the key formula is this. Okay, the key formula is this, and the proof of this is also very easy. Okay, so if f is a function of this, so f is a function of this Brown motion. Okay, so if f is differentiable, and the derivatives in L2, and also the derivative, so this is derivative, and you divide by this. If this one is in the domain of its adjoint operator, so delta is the adjoint operator of this derivative. So this is also a stochastic integral. Okay, so this one depends on t here. If this one is integrable, okay, if this one is in the domain of this, then this one, the probability law. So this is a continuous type of random variable. So this one, the probability law of that is absolutely continuous with respect to Lebesgue measure, and the Lebesgue measure is also bounded, and it's given by this. Okay, you can find the density of this f. So this one is the probability density of this. Okay. So this is a general formula. Okay, so this for any f. So how to find the probability density of a random variable? If this one it has Malliavin derivative, and if this one you can divide by something, this is not equal to 0. Not only this is not equal to 0, this is in LP in some sense. Okay, this is in L2. Okay, this is in L2. Then this one, this is some kind of Scholar integral. Okay, so how to show this? Let me give you the idea here. Okay, so I assume that this one is a Dirac delta function. Okay, Dirac delta function. Then P, any function is given by this. Okay, so if f has a probability density of y, then so this one is exact expectation of this. Okay, so now the Dirac delta function is the derivative of the integrated function. Okay, you take the integrated function and then you replace f here. Okay, so now I consider this f bigger than x, and I take the Malliavin derivative of this. Malliavin derivative of this, so use chain rule because it's a derivative operator. So you differential with this y, which is equal to this. Okay, and then dfy. Okay, so dfy and dfy of this is the same as this. So you get this. Okay, so this one is equal to this. And then now you can move this in because this is the h is something like this, ft gt. So this is your h. So this one does not depend on t, so you can move it in. And then so this one, so delta, this Scholar integral is the adjoint of this. Then you can move this on this side, then you get this. Okay. So this one you use this Dirac delta function. So if you don't want that, you can also prove it more rigorously. For example, for any function, smooth function with compiler support, so I consider this. I just try to compute this. Okay, I just try to compute this. So if this one is equal to this, then you can show that this one, then this by definition, this one is probability density of this y, f. Okay. So for any u, and you divide by this, if this one exists. So if you take this one is df, u equal to df, then you get this formula that I just showed you, okay? For any u, you can choose any u, in fact, okay? So this expectation is, because this is random variable, this is random variable, so this expectation is with this one. So if we exchange, so because these are nice with the common support, these are nice, then you can use the Fubini theorem to put this outside. You can get this, because this d is x is less than f, so the integration is from negative infinity to f, okay, dx. So this one does not has f, okay. So this one has no x, so you just do this one here, okay. So now third, the adjoint operator of this is d. So you put this one on this side, you turn it to d, then you get this. So now you use the chain rule. So differential with this one, you get gf, okay, then df, you get this. Okay, this g you can put outside, because g does not depend on t, so you have t here, okay. So this is ut here, you can get 1, then you get this. So this one, for any g, so this is true, then this one should be the probability density function of this. So this is our definition of this probability density function. Okay. So this formula is essential of the Malliavin calculus. Okay. Okay. So this one. So we use this one. We use this one to show. So we use this identity to show the probability density of this, the low txy. Okay. We use this identity. So this is the essence of Malliavin calculus. Okay. So the main difficulty here. So what's the main difficulty? The main difficulty is to show this one is no this one is so you have to show this one in some sense. You have to show this one negative one or negative p is less than infinity. So this is the negative moments of the Malliavin. So this is called the Malliavin covariance Malliavin. So people call this a Malliavin covariance matrix. Okay, some kind of this. Okay, so the question is how to show this one has so this one has negative moments. So you have to show this. This one is very, very difficult, okay? So this one is the main difficulty in the application of Malliavin calculus. So we have to show for the solution, so we have to show this one has negative moments, okay? So this one has negative moments, and we can bound it by this, okay? So this is the main work. And also, so from here, so then the solution is given by this. So this is Malliavin calculus. So this is the formula. So this is the formula that I showed you before. So the question here is, so it's easy from here to find the upper bound, but how to find the lower bound? Then this formula is very some kind of more complicated to find the lower bound. And for this one, we have to do something more complicated. Okay. I'm sorry that maybe I'm out of time. Thank you. So here is what I want to talk. Thank you so much. Thank you.
Thank you. Thank you very much, Yaozhong.
Thank you. Thank
okay,
you.
So we've got time for questions or comments.
May I ask a question?
Please
Yes.
go ahead, Andrew.
Yeah, so thank you very much. I understand that to solve this equation is really already a very complex problem. But say in many cases, people are interested to consider left-hand side, which is a partial fractional derivative in time. Do you think that it's possible to find solution for fractional cases as well?
Yeah, there are some people work on this. For example, I think this the guy in Urban University. I think he worked on this also. This name. Someone called the name. I can't name. And there are some people work on this fractional one. Yes.
Okay, thank you. And it somehow leads to my main question. So you investigated the density of your solution, but do you have some results about behavior of your solution over time? say, for example, covariance structure or something similar to that. Because usually, if you consider usual differential equations without this additional multiplier u, if you have just first derivative, you have like Wick dependence case. If you have fractional derivatives, you can get long memory and something similar to that. So do you know something about behavior of solutions over time, covariance or similar things?
For fractional
for
time.
Your case. Yeah.
So in my case, there are some work. For example, some people, because we have this bound there, and the people try to find the constant. So for example, we have something like this. For the solution, people found it. So I can't find it somewhere. So people find this. People find say, for example, ut x. People find the p, the ut x p expectation. People find this, and some t to some power. This one is to say this constant. They found this constant when t go to infinity. People find some kind of a large deviation result. This called the large deviation. People find this constant. So 1 with t alpha like this. Look, exponential ut x p so equal to something. People find that this constant when t go to infinity. People found that this constant is given by some kind of the first eigenvalue of something, the first eigenvalue of this operator or something, in some sense. So some this representation form. That's some work, yes. And there's also some work about this when x go to infinity.
Okay, thank you.
Okay.
Any other questions or comments?
May I ask a question?
Please.
Yes.
Go ahead.
Thank you.
Yeah. I have a question about your theorem where you give estimates for the density. Perhaps we can go back to this page. Yes. So formulation suggests that the constants do not depend on x. Is it right?
No, because no, does not depend on x.
And is anything known about behavior of this density as a function of x for fixed y?
Yeah, it's very interesting, very interesting question. Yes. Usually say so if the initial condition is so because if the initial condition is equal to 1,
So
then
this one homogeneous solution.
Yeah, then this one, so the density does not depend on x. But if the initial condition is like a delta function, then then there are some people work on the how this one depends on this x, but not the density. So how this one depends on x. So how this one depends on x, but not the density. Yeah, it's very interesting question. Yes.
And I have one more question. You showed at a certain stage, you showed a formula where Airy function was needed.
Yeah. So this is the work of this people of this Colvin and yes, this Colvin.
Yeah, my question is that Airy function gives you the green kernel for third order differential equation. So is there any relationship or?
Yeah, I don't know because they use this Airy function is from this Tracy-Witten law. It's from their motivation, the use of this is from this random matrix like from there. So not directly from the ODE. So maybe something related to ODE. So I don't know the result here more. So
this is not.
so I didn't go to
I
didn't go to details on this. It's very interesting. It's a very complete result here. Yeah.
Okay. Thank you.
Thank you. Thank you.
Any more comments or questions? No? Well, if not, please join me to thank Yaozhong Hu for
Thank you so much.
very interesting
Thank you.
talk. Thank you.
Thank you. Thank you. Thank you.
And over to you, Kostya, for the next one. So you want to announce the next one or? Kostya, okay.
Probably not announcement now.
No announcement now. Okay.
No.
All right. Well, I look forward to seeing you all again in a couple of weeks' time. All the best.
Okay.
Thank you again, Yaozhong.
Bye bye.
Thank
Take
you
care.
again.
Bye
All
bye.
the best.
Yeah.
Bye.